When asked to find the gradient of a line, you can easily pick any 2 points and then use the gradient formula, which is y2 minus y1 over x2 minus x1. So that's good for straight lines. But what if you have curves? And hopefully you can see that the gradient will intuitively just change. The gradient tells you how y changes based on how x changes, how fast y changes based on how x changes. And you can see that at different parts of a curve, instead of a straight line, the gradient is different. It will be different. If I just take this part of the curve, we can see that the relationship is that as x increases, y increases. So a very rough summary of the relationship. But if I go here, as x increases, y decreases. So the gradient is always changing on curves. Now, we follow a very basic method of using what we know on gradients on straight lines, and we're going to apply it on curves. And this is just the beginning of calculus. So once we get this basics sorted, then we can actually find shortcuts and we can avoid all this mess that I'm doing in the video. But understanding what we do in the beginning is important. So let's say we take just this curve. I just did any cubic curve, and then we want to pick a point A. So I've zoomed in, I picked this random point A on the graph, so on the curve. And then as you zoom in, the more I zoom into this curve, the curve will no longer look like a curve. It's actually going to appear like a straight line. And on the straight line, so this is my point, and on the straight line, I'm going to choose 2 points very close to A. And I'm going to draw a line segment, so a line that goes through the C and B. Now, again, we've picked a point on a curve, but once we zoomed in, it really looks like a straight line. So if I want to find the gradient at this point, I'll just choose very 2 close points, and that's what we usually do when we want to find the gradient of a line. Is that we pick any 2 points on the line and then we do the whole y2 minus y1 over x2 minus x1. So this is what we're doing. So as you zoom out now, we've created this line segment, but as we zoom out, you'll notice that the line actually becomes a tangent. And by definition, a tangent is a line that touches your curve at one point. So it looks like it's touching our main point. So actually, if I want to find the gradient of a curve at this specific point, at only this point, because remember, the gradient will change around the curve, but if I want the gradient at that specific point, all I have to do is find the gradient of the tangent of that point. So this is the definition. The gradient of a curve at a point is given by the gradient of the tangent at the point. And we've seen why, because if I go in, this tangent, it looks, as I zoom in on the point, it looks like a straight line, and this tangent goes through my point as well. So we find the gradient of the tangent, and this process is called differentiating at a point. So if I find the gradient of this tangent, I've basically differentiated the curve. So a bit of a long process, and it seems a bit weird. Do I have to repeat this step every single time whenever I want to find the gradient at every single point? The main thing you need to take from this is that differentiation is basically taking the gradient of this tangent. But how do we find this tangent? You don't have to go through this process. Now, one immediate consequence of this step is to go through what we call the first principle, which is what we use at the beginning before we start with the actual rules of differentiation. Again, these steps are just step up into just using the shortcuts of differentiation in calculus, unless your course requires you to use first principle, which they should mention in questions. But for now, it's quite important to understand how they work together. So understanding this and then moving on to the shortcuts, which are explained in other videos. So using what we've done before, we're going to do the same thing, but instead of taking a point B and C, we're just going to add one additional point B. And we're going to call the vertical distance from X to the point B H. So this is our point x. Let's call this is our main point, and this is our point b. Again, the goal of this is to find the gradient at our point x. So let's call this vertical distance h. So this is x, this is our b, and this blue distance will be h. So therefore, this our main point the coordinate can be called x comma f of x, and then b is basically just taking x and then adding h to it. So the x coordinates of this will be x plus h, and so the y coordinate will be f of x plus h. And you can pause, rewind what I said just to understand why point b is x plus h. So this is x and then plus h, that will give us point b. So the gradient of this, using the exact formula as you've done before with the gradients of straight lines. So again, we have the situation where we've zoomed in, it looks like a really straight line, therefore I can pick these 2 points and say I'm going to find the gradient of this point using these two. So what we're going to do is take, this is our y2 and y1, so we're going to take this minus this, and then our x2 minus x1, so x plus h minus x, that will simplify to h, and you can do that. So this is what we have. So if I want the gradient of this segment, it's going to be this formula, and this is basically just using the formula for the gradient, and this part is basically a simplification of this, which simplifies to h. So now this is not exact. We want it precisely at x. So what we're going to do is we're going to use limits, and what we want to do is we want to actually, as if we're going to just bring b just closer to x and bring it closer and bring it closer until it's very close. So what we want to do is reduce the h distance. We want to reduce the distance until it's almost 0 but not exactly 0. So this is where limits come into hand. And this is what we call differentiating using a first principle. So if I do this process on my function, I'm actually going to be able to find the gradient at this point. And we shorten this process notation using f prime of x, or dy over dx. So this is the derivative of y with respect to x. So I'm going to do a quick example on this. It seems very weird, but it's definitely doable. So if I have this function and I want the gradient at x equals to 3, so our main point is going to be 3. So I'm not going to expect you to find a point B and then draw a segment on the curve. No, we're just going to use first principle. So this is our first principle. And what it tells me is I want you to do f of x plus h minus f of x over h. Do you need to find an h? No. But we know what x is. X is 3. So all you have to do is just substitute this 3 in there. Now, don't feel weirded out. This is basic function substitution that you know how to do. Instead of x, we're going to substitute 3 plus h in here. And instead of f of 3, we're just going to substitute 3 in here. So I'm going to do this. The first part comes from the f of 3 plus h. And then the minus 16 comes from just substituting 3 into this. So simplifying this is going to give me the limit as h approaches 0 of this function, and notice how I have an h in every single term, so I can cancel the h's out, and this is going to leave me with this. Now, using your knowledge of limits, you know that you can immediately just substitute 0 in here to know the limit, and that's going to be 12. So what this tells you is that the gradient at x equals to 3 is just 12. And I can actually look at this and tell you the solution in 2 seconds. I don't even have to go through this process. And knowing the answer really quickly is by using what we call the differentiation rules. And these rules come from us repetitively using the first principle and noticing all these hints and clues and patterns until we were like, okay, don't need to use the first principle, we can just use these quick tricks. But hopefully this video is clear, you understand how all these processes lead up to you actually trying to find the gradient at a specific point. And the basics of differentiation start with using the first principle.